Case 1. When r equals 0. Substituting r in equation 1, we get a equals 3q plus 0, a equals 3q. Now, performing a squaring operation on the both sides, we get a square equals 3q whole square, a square equals 9q square, a square equals 3 into 3q square, a square equals 3m, here assuming m equals 3q square. Case 2, when r equals 1. Substituting r in equation 1, we have r equals 3q plus 1. Now, performing a squaring operation on the both sides, we get a square equals 3q plus 1 whole square. Recall the identity, a plus b whole square equals a square plus 2ab plus b square. Here a equals 3q and b equals 1. A square equals 9q square plus 6q plus 1. A square equals 3 into 3q square plus 2q plus 1. A square equals 3m plus 1, here writing m equals 3q square plus 2q. Case 3. When r equals 2. Substituting r in equation 1 gives, we get a equals 3q plus 2. Now, performing a squaring operation on the both sides, we get a square equals 3q plus 2 whole square. Recall the identity, a plus b whole square equals a square plus 2ab plus b square. Here a equals 3q and b equals 1. A square equals 9 square plus 12q plus 4. A square equals 9q square plus 12q plus 3 plus 1. A square equals 3 into 3q square plus 4q plus 1 plus 1. A square equals 3m plus 1, where m equals 3q square plus 4q plus 1. Hence, from all the three cases it can be said that the square of any positive integer is either of the form 3m or 3m plus 1. Note, this problem can also be solved in a easy manner as follows. Alternate method. As we need to show that square of any positive integer is of the form 3m or 3m plus 1, we are taking the smallest positive integers from 2 onwards. Square of the positive integer 2 is 4 is equal to 3 into 1 plus 1, which can be written as 3m plus 1 for some integer m. Square of the positive integer 3 is 9 is equal to 3 into 3, which can be written as 3m for some integer m. Square of positive integer 4 is 16 is equal to 3 into 5 plus 1, which can be written as 3m plus 1 for some integer m. Similarly, for any other positive integer, the square of the integer will be of the form 3m or 3m plus 1. Example 6. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Solution. Let a be any positive integer, and b equals 3, as 9m plus 1, or 9m plus 8, is of the form bq plus r, by Euclid's lemma. We know that a equals bq plus r, where 0 is less than or equal to r less than b. Then, a equals 3q plus r for some integer. Q is greater than or equal to 0, make it as equation 1. Since 0 is less than or equal to r, less than 3, the possible remainders are 0, 1, and 2. Consider the following three cases for r equals 0, r equals 1 and r equals 2. Case 1, when r equals 0. Substituting r in equation 1, we get a equals 3q plus 0. Now, performing cubing operation on both sides, we get a cube equals 3q whole cube. A cube equals 27q cube. A cube equals 9 into 3q cube. A cube equals 9m. Writing m equals 3q cube. Case 2, when r equals 1. Substituting r in equation 1, we get a equals 3q plus 1. Now performing a cubing on both sides, we get a cube equals 3q plus 1 whole cube. Recall the identity, a plus b whole cube equals a cube plus 3a square b plus 3ab square plus b cube. Here a equals 3q and b equals 1. A cube equals 3q whole cube plus 3 into 3q whole square into 1 plus 3 into 3q into 1 square plus 1 cube. A cube equals 27q cube plus 27q square plus 9q plus 1. A cube equals 9 into 3q cube plus 3q square plus q plus 1. A cube equals 9m plus 1, writing m equals 3q cube plus 3q square plus q. Case 3, when r equals 2. Substituting r in equation 1, we get a equals 3q plus 2. Now performing a cubing operation on both sides, we get a cube equals 3q plus 2 whole cube. Recall the identity, a plus b whole cube equals a cube plus 3a square b plus 3ab square plus b cube. Here a equals 3q and b equals 2. A cube equals 3q whole cube plus 3 into 3q square into 2 plus 3 into 3q into 2 square plus 2 cube. A cube equals 27q cube plus 54q square plus 18q plus 8. A cube equals 9 into 3q cube plus 6q square plus 2q plus 8. A cube equals 9m plus 8. Writing m equals 3q cube plus 6q square plus 2q. Hence, from all the three cases it can be said that the cube of any positive integer is either of the form 9m plus 1 or 9m plus 8. Note, this problem can also be solved in a easy manner as follows. Alternate method. As we need to show that cube of any positive integer is of the form 9m plus 1 or 9m plus 8, we are taking the smallest positive integers from 3 onwards. Cube of the positive integer 3 is 27 is equal to 9 into 3, which can be written as 9m, for some integer m. Cube of the positive integer 4 is 64 is equal to 9 into 7 plus 1, which can be written as 9m plus 1, for some integer m. Cube of positive integer 5 is 125 is equal to 9 into 13 plus 8, which can be written as 9m plus 8, for some integer m. Similarly, for any other positive integer, the cube of the integer will be of the form 9m plus 1 or 9m plus 8,